The goal of this video is to show how to implement proportional control of our DC motors. Instead of starting completely from scratch this time, I have a bit of skeleton code here that we'll fill in. Also, since last class period, I've learned a little bit more about how JAG packages local, or how you're supposed to install local packages using JAG. So the syntax here is a little bit different depending on how we're going to use files. The local files denotes things that are not that don't have any dependencies. Local packages are anything that do have dependencies, and we're trying to make those easier to use so that you don't have to copy over those package.yaml files like I was showing in previous videos. So the syntax for importing in TOIT is to say import and then the name of the package. And this is an underlined red squiggly because it doesn't know where to find this package. We'll have to tell it where to find this package. And then you can import specific names from that package instead of just implementing the entire thing or having to use the prefix. So for example, I didn't want to have to say communication dot communicator everywhere. Instead, I just want to use communicator bare like this, which is why I have communicator after the show keyword. So that's a good place to start. Let me go to a terminal, and inside this new file, inside this new directory, I just have this skeleton code that we'll start filling in. And the first thing I'm going to do is to say jag package install, and I'm going to install from a local directory. What this did for us is it created a package.log file, a package.yaml file, and we can view either of those. You can see the package.yaml just lists the dependencies, one of them being the path to this local directory, and then a hidden directory that we're not actually looking for, this .packages directory. And if we were to look into there, you would see the HTTP package, which is something that my communications library or communications package depends on. So now, without having to copy over the package.yaml file, we should be able to get rid of these errors. And we should also not have any missing dependency issues that occur when you try to do jag run without calling jag package install first. I think all that needs to happen now to have this get rid of the squiggly underline is to restart the language server. I probably could trigger it to, could probably trigger it just by starting to type. It probably restarts the language server, or the language server tries to pick up new information each time you type. Alright, that's the only dependency we're going to use this time. I'm going to skip the display. That's something you can do in your own code if you'd like to. And I'm going to call our communicator, the thing that implements communicator, the heartbeat handler. And this is really just going to be in charge of halting the motors whenever we lose communication or whenever somebody purposely disconnects. And what we'll focus on in this video is implementing proportional control, a motor controller, which I could really put those into a single class if you wanted to, but I'm going to split them out for reasons that'll become apparent as we start to fill them in. And then we'll fill in the main section here. Currently, all that happens is code you've seen before. We wait for the heartbeat handler to be enabled, and at the end we make sure we stop the motors and then just print done. So we'll fill in some code here in the middle as well. Let's start with this proportional control class. This is going to implement that equation that U equals Kp times E. So it makes sense that this has a Kp member variable, and that's something that needs to be initialized in the constructor. And the way to initialize a variable in TOIT is by putting a dot and then Kp. And that's essentially shorthand for something that might look more like this. So we could do that either way, but we'll go with what TOIT considers best practice here. And I think I'll turn off GitHub Copilot so I don't get so many confusing text just popping up all over the place. All right, next let's start looking at implementing this equation. And I'll call it compute speed for now. To compute the speed, we'll need to first compute the error, which would be something like the desired speed minus the measured speed. So those will be parameters that we need to pass into our compute speed method. With error, we can now compute u, and that'll be kp times error. As I mentioned in the slides from the previous chapter, we're not going to use u directly. Instead, we're going to use u to compute speed instead. And in particular, we'll do something like this. And as you can see, I don't already have a value for speed that I'm just hanging around, so we'll also have that be something we save. And I can initialize that to 0 without having to do so in the constructor. I'd encourage you to think about why we don't just use u directly, and instead we're accumulating u, essentially. And your hint here is to think about what happens when I have an error of 0, and what do I want the PWM to be, or what do I want the speed to be? How do I want them to change? In the meantime, this is close to what we want. However, there are a couple of things we'll want to change here. The first being, we don't want u to change too drastically from one time step to the next. You can imagine we said go 20 centimeters per second forward, and then immediately we said, okay, you should actually go 20 centimeters per second in reverse. And so that would create a 40 centimeter per second error. And the larger the error, the larger the change that we're going to impact on speed. And it's not really good on your motors to have them in full forward and then full reverse. So we're going to limit how far you're allowed to change the control variable here, u, from time step to time step. And for that, I'm going to introduce a new function called constrain. Constrain is implemented in this new utilities file that I'm giving everyone. And the error here is that I haven't given it enough values. So we could say, for example, we want to constrain the value of u between -1 and 1, for example. And it wants those to be floating point values. One thing that makes this a little bit difficult is that TOIT, the programming language, doesn't use parentheses or commas to separate variable arguments. So it might help if you have an equation like this to group it and make it easier to see that constraint is taking 3 values. The current value of u, the low end that we're constraining to, and the high end. Now, for now, I just put -1.0, but that's really something that we'll want to configure and find a good value for that. So as a way to document that that's a variable we want to update and change, I'll add it to the class. And we'll call that the maximum speed step. That's going to be a float, and we'll make the user specify it. Whoever's creating the proportional control class or object needs to be prepared to pass in a maximum speed increment. And we'll allow them to have anything sort of on the negative up to the positive value for that range. So if that value is 1, we're going to allow, we're only going to let error values jump sort of in the -1 to 1 centimeter range. If it's -20, it'll be clipped to -1. That's one change. Another change we'll make is that we want to put limits on the speed that somebody's allowed to set. So we can use constrain again. And we can say they can go from max speed, negative max speed to max speed. And clearly that's not something I've specified. So I'll need to add it. One other thing we can do to protect users from themselves is, now that we have a maximum speed we're allowed to go, we can make sure that the desired speed is also not outside of that range. This isn't strictly necessary. We could just document this, but it doesn't hurt to make sure that we never have our desired speed outside the range that's reasonable. Separate from our proportional control class, we have our motor control class. This is the object that's directly responsible for actually updating the motors themselves. So it'll need access to the motors. So we'll make sure that whoever creates a motor controller object passes in the motors that are going to be controlled. We also want to create two proportional controllers, one for the left side and one for the right side. For both of those, we need to initialize the value for KP, the value for max speed step, and the value for max speed. For now, for lack of a better way to do this, I'm going to just make those constants. And this can be the place where you change them. You could also change them in main and pass them into motor control. I don't know that there's necessarily a best way to do this. So we'll have a proportional constant for the left motor and a separate one for the right motor, and you'll have to tune those separately. And for now, let's just say the maximum speed that we can step is 0.1. We'll find out that that's a little bit on the slow side. And I'm going to say that our maximum speed that our robots can reach is, let's say, 40 centimeters per second. That's just arbitrarily chosen. That's something that you'll want to have already computed for yourself, using the methods that are mentioned in the previous chapter. Now that those are defined, we can finish constructing our motor controller objects. Finally, the last thing this motor control class needs to do is update the motors. So let's call that update, and I'm going to call it forward speed. We'll call it forward speed because for now, let's not worry about turning or do anything more fancy than just going straight forward. The user of this class needs to pass in the speed that they want the robot to go. And now we need to start filling this in. So we want to update the left motor and also update the right motor. What does it mean to update the left motor? First, we'll want to compute the measured speed. So we'll want to after we have the measured speed, we'll want to set So let's work on this one step at a time. The first thing to do is to get the measured speed for the left motor. So how do we figure that out? That information can be gathered from the motor encoders. So we should be able to say, from our motors, we can get the left encoder and get the rotation rate from that encoder. If I look at the definition of this function, you can see that I'm required to pass in a time delta, and that is used to compute a rotation rate. So we need to know how much time has passed since the last time we checked the motor encoders. For that, we need to compute, let's call it a time delta. And the way to compute that is to figure out how much time has passed between now and the previous time that we checked the motor encoders. So we can call that something like left time. So first we need now. And TOIT has a built-in function called time monotonic, and that gives us something back in microseconds. So we'll have to take that into account. And we simply need to store the previous time. And we'll initialize left time inside the constructor. Time delta now is a time delta in microseconds, though. So let's convert that to seconds. And seconds are going to be a real valued number, so we'll convert it into a floating point number before using it. At this stage, what we've computed is actually just the rotations per second of that motor. So this would be better renamed as left rotations per second. To convert that into motor speed, we would need to know the rotations per second and the wheel circumference. And hopefully that's a constant for you. So we'll add it here as another constant. And for my robot, it's 7 centimeters. Now that we have left speed, we can, I'm missing a step here, compute the next output. We can use our proportional control class, our left controller, and call the compute speed method. The compute speed method takes a desired speed and a measured speed. And that's going to give us a value back. I'm just going to call it speed for one moment here. And finally, the last thing we need to do is grab our motor and set the speed for it. And we have a few different ways to set speed. We have the set direction, which doesn't change speed. We can set the duty factor, which does actually change speed. And I'm noticing a few duplicates here. I wonder if I need to jump into my motor class and see what it's been renamed to. Looking through our options here, a few of those I'm not sure why the language server is picking up more than it needs to. We have set direction, set PWM duty factor, and set speed factor. Those are really the only options we have for setting the speed. For setting the speed, it's really just these two, setting the PWM duty factor or setting the speed factor. Setting the speed factor is probably a nicer interface because it handles both the speed and the direction. So that's what we'll want to call set speed factor. And this function takes a single value in the range -1 to 1. Whereas our speed here that we're getting back from our left and right controllers are values between negative max speed and positive max speed. So for that reason, we're actually going to make a change. We can make this change in multiple places, but what we're going to do, and what makes our code the easiest to write and reason about, is just to change our proportional control to set a speed factor instead of a speed itself. This is now going to be a speed factor, and we'll return a speed factor. And instead of being from max speed, negative max speed to max speed, it can really just be in the range -1 to 1. The final thing to do is to change the name of our variable here. Now you might notice something a little odd here, which is we are doing a bit of a translation inside this function between speed factors and speed itself. We have error, which is in units of speed, and then we have u, which is in units of speed because we have error, and it's also capped between a min and a maximum value. But this constant factor here, kp, we could really assign any units to that we want to. So in this case, we're essentially assigning the units needed to convert centimeters per second into our speed factor of going from -1 to 1. I always think it helps to sort of do those mental gymnastics, even if the code doesn't actually change. It's useful to assign that discrepancy between the two possibilities to the variable kp, the constant kp. Jumping down into our code, we need to rename this factor, rename the variable that computes the or gets the output, and then finally actually set the motor's output. Our next step is to repeat the entire process for the right motor. I would encourage you to not do what I'm about to do. I'm just going to copy and paste code. I would encourage you to take all this code that's duplicated and put it into its own method, something between the constructor and the update forward speed function. For expediency here, I'll just pause the video and duplicate all the code necessary. Or actually, it's probably instructive to show how I would duplicate it. I'll just duplicate each line. And then for some of the values, I'll just change the value of left to right. Let's see, we need a value of left here. And the complaint here is that when you do colon equals, that's supposed to be introducing a new variable, but I already have now and time delta introduced above. That's okay. I can just reuse the same variables but assign new values to them. All right, we now have a motor controller based on two proportional controllers, one for each motor. Our final step here is to figure out how to use this class, this object. Sensibly, probably the first thing we should do is create a motor control object. And to create a motor control object, we need to pass in our motors. Next, we'll also want to set a speed. Let's say that we want it to go 20 centimeters per second. It would also make sense to have a certain time that we wanted it to run for. So I'm going to set a duration in milliseconds, and let's say it's 10 seconds. We also need to know how frequently we want to update our motor's output. If we were to go through this once and just change it once during the 10 seconds of running, the motors would be updated one time, and we would ever actually use the feedback to update them additional times. So the way that I've written our proportional motor controller with all these constraints, it's likely our motor would just never get up to speed, the speed that it needed to. So we'll want some constants for how frequently we want to update. And let's say we do it 10 hertz, 10 times per second. That might be a little on the slow side, but it should work well with TOIT and JAG. Let's have a while loop that runs for our duration. And inside the loop, we'll update the motors and then sleep. That'll be a pretty common pattern that you'll see as we're using JAG and TOIT. It's important to sleep because that will yield this thread of execution and let other threads run if they need to, other fibers. Actually, let's do all of our time in milliseconds. So to update our motors, we have our motor control object. We'll call update forward speed, and we'll pass in our desired speed. Finally, we will sleep for our control update timing. All that's left to do is to run this and see how well it performs. I just plugged in the microcontroller, and we'll start by doing a JAG monitor. I'm lucky enough to have it connect to Claremont ETC quickly. Let's see, I'll start by setting the IP address. And it looks like I have a different IP address than the last time I ran this. 172.28118.49. Alright, my code is uploaded, and now it's waiting. We're currently stuck in this loop here. Every second it'll wait for the heartbeat handler to receive some sort of message and start running. So I'll turn on the motors. And we'll send a message. And my port is 6718. The motors ran for 10 seconds and then ended. One thing you might notice is that, given the way I've written this code, it doesn't work in quite the way we might hope. I use WSCat, which just sends a single value. If I had become disconnected, maybe WSCat crashed without sending a disconnect signal, I'd have no way to stop this thing from moving. And that's because even though the disable is being called, which is calling halt, which is calling motors.stop, my code is always overriding that on motors.left motor setting the speed, and same thing here. So one additional thing we want to add to this is we want to continually check that the motors haven't become disabled. So while heartbeat handler dot is enabled. And hopefully you'll believe me that that works. I'll leave the video here since it's already a bit longer than I normally would have anyway.